Hi guys, we're back in Chemistry 1001, Thermochemistry and Thermodynamics. This short little video is going to show you how to calculate delta H for a reaction if you have other reactions that can be used to add up to it. So the title is Using Enthalpies of Combustion to Determine Delta H from a given set of reactions. So let's have a look at how that works. Here's the problem. We're hydrogenating graphite. So we've got graphite, which is just pure carbon, and we're reacting it with hydrogen gas. And the reaction's shown over there. 3 carbon atoms reacting with 4 hydrogen molecules to give you C3H8, whatever that is. That's the reaction. And the data we're given are combustion reactions. Carbon burning in oxygen gives you CO2, hydrogen burning in oxygen gives you water liquid. C3H8 burning in oxygen gives you carbon dioxide and water, and there are the heats of reaction on the right hand side there. They're all negative, so they're all exothermic reactions. The delta CHEM is just another word for delta reaction, and these are standard heats of reaction. So they're occurring at 1 bar pressure. We don't actually know what the temperature is, but probably 25 degrees. It's not given to us in this problem. Okay, so how do we calculate delta H for the first reaction if we are given these 3 reactions on the bottom? Well, one way is to use the idea that we can combine all the combustion reactions in a particular way to get the result we need. But I'm going to look at the second way to do it, which is more easy. We combine the reactions with appropriate stoichiometric coefficients to get the one we want. So we have 3 carbons on the left, and here we have a reaction. In fact, it's the only reaction with carbon, but there's only one. So the only way we can add these 3 reactions together to get this first reaction is to take 3 times the first reaction. So here we have the first reaction, all times 3, and we note that the delta H for 3 lots of this reaction is 3 lots of the single reaction. So 3 times 394 is the delta H for 3 lots of carbon with oxygen combusting to give you 3 lots of 3O2. Okay, the next reaction, we have H2 going to H2O liquid. We look at the above reaction here, and we have 4 lots of H2 on the left hand side. Here we have 2 lots. Well, in fact, H2 only appears over here in the second reaction on the left, so we have to multiply that reaction by 4 in order to get the 4 hydrogens here, and that's what we've done in this reaction over here. And finally, this last reaction, we have a C3H8 on the left hand side. Unfortunately, we don't have a C3H8 on the left hand side, but we do have it on the right hand side. What we can do is we can reverse this reaction, and when we reverse the reaction, the delta H becomes opposite. Instead of a combustion reaction, it's an anti-combustion reaction. It's a bit difficult to imagine an anti-combustion reaction, but in principle it's possible to do it. In fact, we'd love to be able to do that, to get rid of carbon dioxide from the atmosphere. If only we could do this. We can do it if we use special catalysts and we use a lot of energy. In fact, we'd have to use 2,220 kilojoules to convert the carbon dioxide with the water back into C3H8 after it's been burned. Exactly the opposite of the energy of burning. Anyway, we reverse this reaction so that the C3H8 appears on the right hand side where it should be, and that means this delta H has to be multiplied by -1. So we add these delta H's together and we get the net delta H for this reaction. Now you're probably wondering, well, what about the oxygens? Do they cancel out? In fact, they do. The only way that you can get this reaction to occur by cancelling out the oxygens is in this way. And that's because the reactants appear only once on one side of the reaction. So this is a special kind of a case. And that's how you do it. Now you can try it yourself.